We've been talking about kinetics. Kinetics is the study of reaction rates and the factors that affect them. We'll be talking about one factor in particular today, which will be concentration. To understand how these factors affect reaction rates, you need to understand the collision theory. So we're going to be spending some time on that today. We're going to learn how to write rate laws, which differ from rate equations, the rate equation you wrote in the Do Now. And we will learn how to write and interpret rate laws today, very simple ones, and then we'll get involved in much more complicated ones next time. And later in the week, we'll draw and interpret reaction profiles. So where we're going to pick up is right here. We're going to look at the factors that affect reaction rates. So again, kinetics is the study of reaction rates and the factors that affect those reaction rates. We're going to look at the factors today. Before we get into the collision theory, we want to make a list of factors that affect reaction rates. So the factors that affect reaction rates. First thing you want to consider is the nature of the reactants. The reactants must be compatible in order for them to react with one another. If you put an iron nail next to aluminum foil, there's not going to be any reaction between those. Metals don't react with one another. For example, we said with the lab on calorimetry, salts don't burn, so there's not going to be any reaction between them regardless of what you might do to concentration, temperature, surface area, etc. So what the reactants are is the most critical factor, because if the substances don't react, nothing you do is going to alter reaction rate. Another factor is the concentration. That's the one we're going to look at today, and we'll be looking at the lab in regard to concentration as well. That's going to be concentration with the unit of molarity, moles per liter. With concentration, we're going to understand the effect of concentration on reaction rate through what's known as a rate law, and we'll introduce rate laws today. You also can see it in regard to reaction mechanisms. That's a little bit advanced for the honors level. We're going to look at temperature. We've done several labs this year where we heated the reaction to increase reaction rate. And we'll talk about why temperature affects reaction rate. Another factor is the surface area. In many labs that we have run this year, we have used powdered substances or substances that have been grinded as opposed to just a sheet of substance or a cube, etc. And you will see that surface area affects reaction rate. The other factor would be a catalyst. A catalyst is a substance that increases the reaction rate by providing an alternative mechanism where the activation energy is lower. We'll get into that more toward the end of the chapter. Last year you learned about enzymes. We talked about this the other day. Enzymes are biological catalysts. Without enzymes, you would not be alive. These are factors that affect reaction rate, and we're really going to focus quite a bit on concentration to get it going. Before we talk about any of these factors, we want to understand the collision theory, because the way you explain how these factors affect reaction rate is through the collision theory. So we're going to take a look at that. In regard to the collision theory, you will see that reaction rates will depend on effective or successful collisions between particles that react. Two things must occur in order for a collision to be successful or effective. How many of you have broken a bone? What'd you break?
Ankle.
Your ankle. And how did you do it?
On a trampoline.
So you were jumping and your ankle just turned and you put all of your force and snap it went, right? Perfect example. So, in order to have an effective collision, if you will, in order to break that bone, she was jumping very hard. Significant amount of force. All of your body weight in addition to the extra height from the trampoline by jumping, and you came down and it snapped. That must have been very painful. In order to break the ankle, you needed proper orientation. The foot had turned, I'm guessing, like here's your foot, and it had collapsed, in or out, probably in. And so now her foot is turned, and here's her ankle, if you will, turned in the wrong direction. So that part hits the trampoline. So the ankle had to be oriented to the trampoline properly, because if she hadn't turned her foot in, she probably wouldn't have broken her ankle. Or if she realized that her ankle was cockeyed in the air, she might have tried to break her fall with a hand. So then she might not have broken her ankle, she might have broken her hand or wrist, etc. Usually kids will say they broke their wrist, however it might be. With little kids, they don't have those old-fashioned jungle gyms anymore, what looked like a dome, because the kids would climb on the inside and they would invariably lose their grip and they would fall and they would break their bones. And it's a buckle fracture. My daughter did it off of monkey bars. 1 minute she's up, the next minute I just saw her falling. I'm like, oh gosh. And then you hear the scream. And sure enough, the wrist hit the ground, a lot of force. Even though she probably only weighed, I don't know, maybe 40 pounds at that point. She was little, 6. So, but her wrist hit in such a position that it just snapped. So when you are looking for an effective collision, within that collision you must have the correct amount of force. So you got to hit hard, and you must overcome the activation energy. I added that in your notes here. It's not going to really make sense yet, but at the end of the chapter, when we do the reaction profiles and diagram out the activation energy, it'll make more sense. The other thing that must occur is the molecules must collide in the proper orientation. So in order to have a successful collision, the force must be significant to overcome the activation energy, and the molecules must be oriented in the proper orientation. I'm not saying do this at home. It's a terrible idea, but in the event you were trying to give yourself a concussion, you might run into the wall head first. You'd have to hit the wall hard, and your head would have to be down. And if you were doing this in the last minute, you actually thought about it and said, oh boy, this is a bad idea. You might pick up your head and put your arm out at the last minute. You're not going to get the concussion. You might get the broken wrist or the broken arm, dislocated shoulder, whatever. But because you pulled up at the last minute, this is one of the reasons why in football they do not allow helmet to helmet anymore, because so many of the guys were getting concussions. So they're trying to change the orientation so that that collision isn't successful. In chemistry, enough force, orient the molecules correctly. Any kind of change that affects how many effective collisions occur will affect reaction rate. Shown in this example here, you've got a decomp reaction, and I'm going to pull the slide up for this. You have it in your notes, but it's hard to blow up, so we're going to go off this. So here's your reactant. Here are your products. In order for this reaction to occur, this molecule and this molecule must collide. They must hit each other hard. They hit hard here. However, one of your products is chlorine gas, Cl2. So in order for that collision to be effective, not only do they hit each other hard, but we have to turn this molecule 120 degrees so that this chlorine atom is here. Because now when it's here, chlorine hits chlorine, these two will bond together, this bond will break. This is going to be a successful collision, enough force with proper orientation, and now you've got products. Here you don't get products, you go back to reactants. This collision was unsuccessful or ineffective because the molecules weren't oriented properly. Anything that increases the likelihood of an effective collision will increase reaction rate. So going back to these, and we'll discuss them in more detail, but let's talk concentration. If you were all in this room and I moved all the desks out and you were blindfolded and running around, a successful collision would be one shoulder to the other, and it's got to hurt. So you have to hit each other hard enough and your shoulders have to be oriented properly. The likelihood of a successful collision with 30 of you in here running around blindfolded is not great. You might be hitting each other hard, but if your shoulders are not oriented properly, keep in mind there are many different height differences in here. So for example, if I'm running around and trying to hit some of you who are 6'2", the chance of your shoulder hitting mine are slim and none. So you're not going to get a successful or an effective collision. Now if we invite 4 other classes with 30 kids each in here, now all of a sudden we're up to about 150 kids. Now the likelihood of an effective collision is greater. So with an increase in concentration, in most instances you will increase the likelihood of an effective collision, you'll increase reaction rate. As you increase temperature, what happens to the velocity of particles? Do they move faster or slower? Faster. And this is one of the reasons, especially as a new driver, you shouldn't be driving with pedal to the metal. The chance of an effective collision increases greatly. As particles move faster, the likelihood of an effective collision will increase in reaction rate. With an increase in surface area, one of the reasons that we use powdered substances very often is they go into solution faster or they react faster. That's because powdered substances have greater surface area. You have more sites with which to get an effective collision, increase the likelihood of an effective collision, increase reaction rate, and catalysts will hit later on. But this is an unsuccessful collision, and this is a successful collision. Any factor that increases the likelihood of an effective collision will increase reaction rate. So one factor we said is concentration, and we mentioned, generally speaking, an increase in concentration increases the likelihood of an effective collision, hence an increase in reaction rate. To understand the effect of concentration on reaction rate, chemists have derived rate laws, which we're going to learn about now, just the beginnings, and reaction mechanisms, which I'm not going to go into at the honors level unless you want to do a special lesson on that. It's one of my favorites. I'd be happy to do it with you guys at the end of the week. A rate law is grossly different from a rate equation. Looking back at our do now, we wrote a rate equation right here, where in a rate equation you can have reactants and products, or just reactants, and you have rates of appearance and rates of disappearance, so molar per unit time, let's say molar per second. A rate law is very different. A rate law is an expression for reaction rate as a function of concentration of one or more reactants only. No products in a rate law. Concentration, unit molarity. Unit molar, however you want to state it. For example, a rate law with one reactant only, so you've got 3 moles of A being converted to C. Here's an example of a rate law. A rate law says rate is equal to K. K is a proportionality constant. You can solve for K. We won't this year. The units of K are highly variable. Not going to worry about units of K this year. For your rate law, you will just put a K in there, lowercase k. Times the concentration. Remember, these brackets here mean concentration. You must have brackets like that. Concentration of reactant, never a product in a rate law, raised to the N. N is the order with respect to A. The order will help explain how altering concentration of A affects the rate. N is determined from data, not the coefficients in the balanced chemical equation. Be careful there. There's a specific way to determine the order. N typically is a small positive integer, 0, 1, 2, 3. However, be careful. It can be negative. It can be fractions. You won't get those this year. 0, 1, 2, 3, 4, 5, 6 is probably as big as you'll go. I want to go over how to interpret the rate laws, and then I'll show you how to write them. There's a lot of gobbledygook here. I'm going to do it in a very simple way so that you can follow it. You can scribble it on the side there. I'm going to write some stuff out for you so you truly understand how to interpret rate laws. Again, a rate law will look like this, where you have rate is equal to K, concentration of reactant, or sometimes more than one reactant, raised to the N. N is the order with respect to that reactant. So let's make this a little simpler. Let's say rate is equal to K. We'll say A is our reactant raised to the N. That is a rate law. I'm going to number these how they're numbered in your notes. If N is 0, we have 0 order with respect to A. So that would mean that we have rate is equal to K, concentration of A to the 0. Any number, variable, etc. to the 0 is equal to what? 1, not 0. So that means that the rate is equal to K. That's our rate law. Is concentration in that rate law? No. So if you alter the concentration, will you affect the reaction rate? No. So 0 order. What you have in this particular instance is regardless of any change in the concentration of reactant A, there is no effect on reaction rates. So this would be one of the few instances where altering the concentration does not affect reaction rate. Come on, Gavin, you've got this.
I'm listening.
All right, so in B, if n is equal to 1, we have first order with respect to A. So we would have rate is equal to K, concentration of A to the 1. If the concentration of A is doubled, then rate is equal to K. We're going to put a 2 in here because we doubled it. 2 to the first power is 2. So therefore, the rate doubles or increases by a factor of 2. The rate basically does whatever it is that you've done to the concentration for first order. If the concentration of A is halved, now I'm going to put a half in. Therefore, the rate halves or decreases by a factor of 2, which is the reciprocal of this. So if you get a fraction less than 1 as your rate, the rate decreases by a factor of the reciprocal. So let's say, for example, that the concentration of A is quartered. What would happen to the rate? It would decrease by a factor of 4. So that's first order. And then last, let's say if n is 2, that's second order with respect to A, so the rate would be equal to K, A squared. So if the concentration of A is doubled, we'd have rate is equal to K. Instead of the A, we'll put a 2 squared. What's 2 squared? 4. Therefore, the rate increases by a factor of 4, or the rate quadruples. If the concentration of A is quartered, we've got rate is equal to K, 1/4 to the second power. What's that? 1/16. The rate decreases by a factor of 16, the reciprocal of what you calculated. And that's how you interpret your rate laws. The order lets you know how altering the concentration affects reaction rate. And what we want to learn how to do is we want to learn how to write very simple rate laws today. We'll get into the far more complicated ones next time. This takes practice, You've got to be good in terms of exponents. Let's take a minute to review that. 2 to the 0 is 1. 2 to the 1 is 2 to the 2 is 2 to the 3rd, and 2 to the 4th, and 2 to the 5th, 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4. That's good. What is 4 to the 3rd?
64.
Cool. All right. We are going to learn how to write rate laws. This is going to look hard. I promise my students are always very strong at this as long as you know exponents. We're going to learn how to write a rate law. So from data, we're going to figure out a rate law. It says write rate laws for the following. Here's my reaction. What I'm trying to figure out here is what the rate law is. I know it's going to be rate is equal to lowercase k, concentration of A, to some power n. I'm trying to figure out what the n is. I do this from data, not from coefficients in a balanced equation. This is a rate law. Be careful with the nomenclature. I look at the data. Typically, you will be given several experiments, probably 4. You'll be given concentrations of reactants. You'll be given rate of formation of one of the products. From this data, we can determine the rate law. We're trying to figure out n. My approach is always to look at the data. It's very simple when you only have 2 experiments. And what I will do with only 2 experiments here is I will look for the larger concentration, because I think it's easier to play exponential math when I have whole numbers, not fractions. There'll always be a few kids who want to do fractions. As long as you do it correctly, that's fine. I see that this quantity is larger than this one. So I'm thinking numerator, I'm thinking denominator. The way I do this is I put the concentration of the reactant from experiment 2, because it had the larger quantity, over the concentration from experiment 1, raised to some power n. I typically start with n. When you have more than one reactant, you'll do n, then m, then l, then k. I'm going to set that equal to the rate of the second over the rate of the first. I do it that way because I had the second experiment's concentration over the first. So these numbers have to match. Otherwise, you're going to make an error. Now I'm going to plug those quantities in. I've got 0.4 molar over 0.2 molar to the n, 4 molar per second over 1 molar per second, which I got from here. This over this is 2 to the n. This over this is 4. You can see the units cancel. N is equal to 2. 2 to the second power is equal to 4. So n is equal to 2. We have second order with respect to A. So now from that rate law up there that I'm trying to figure out, I replace the n with a 2. Now I can interpret it. If the concentration of A is halved, I'm going to put a half here. What's 1/2 squared? 1/4. So the rate is either 1/4 what it was, or it's easier to say that it decreases by a factor of 4, which is the reciprocal here, just like we just did. So from data, I can derive the rate law. If A is tripled, what happens to the rate? 3 squared is 9, so the rate increases by a factor of 9. It's 9 times as fast. Let's look at one where we have nothing and see if we can write the rate law. I've got 4D being converted to 2F. I've got 2 experiments. I've got concentrations of D. I've got rate of formation of my product F. It says use the data above and write the rate law. All right, let's take a look. I'm going to rewrite some of this out so that you can clearly follow. I think some of you have already scribbled down the answer, and that's fine. Just need to make sure you're understanding the basis here. We've got experiment 1 and 2. We've got the concentration of D as either 0.20 or 0.40 molar. We've got rate of formation of F in molar per second. It can be molar per minute. It doesn't matter. Just look at what they give you. Here they give you molar per second. This is all given. I'm trying to figure out the rate law where I have rate is equal to K, reactant concentration to the N. So now I'm going to work it. And again, I see this number or this quantity is larger than that, so I want it in the numerator. It's easier. I'm going to have the concentration of D in experiment 2 over the concentration of D in experiment 1 raised to the N. That's equal to the rate of the second experiment over the rate of the first experiment. I've got 0.40 molar over 0.20 molar to the N, and that's equal to 8 molar per second over 1 molar per second. I've got 2 to the N is equal to 8. What's N? 2 to what power is 8? 3. Be careful. Some of you whispered 4, and that's a no-no. So N is equal to 3. So my rate law is rate is equal to, don't forget the K, reactant to the third power. That's my rate law. Make sure you understand that this is a rate law. A rate law helps explain how alterations in concentration of reactant affect reaction rate. 2 interpretations that are asked here. It says if the concentration of D is halved, throw a half in. 1/2 to the third power is 1/8. So the rate, you've got a number less than 1, so the rate decreases by a factor of 8. And then it says if the concentration of D is tripled, 3 to the third power is 27. The rate increases by a factor of 27. That's how you write the rate law. That's how you interpret it. Concentration is one factor that affects reaction rate. By increasing concentration, in most instances, you will increase the likelihood of an effective collision, increase in reaction rate. Rate law, as opposed to a rate equation where they gave you this generic reaction, a rate equation would be something like this. Don't confuse the two. So this is a rate equation or rate expression. This is a rate law. Question?
What does the 4D yield to?
That's just your reaction. Yeah, just your chemical reaction. I just rewrote it so you knew where that was coming from. In your classwork, I believe I had assigned you 1 through 4 already. The only 2 problems that go with what we did today are 5 and 6. And that's because we're going to be getting into rate laws where you have more than one reactant. And we're going to learn how to write rate laws from a series of experiments. It looks very challenging. With practice, you'll be very strong at it. But this is what we're going to be getting into next time, where we're writing rate laws when you have more than one reactant. You could have 2, 3, 4. I don't think I'd give you anything more. I don't even think I'd give you a 4. That's challenging. But I figure if you can do that, you can do anything. And you're better off going through a whole bunch of examples and mastering, so when you get to the quiz or test and it's easier, you do well and you're happier. Questions. We'll be exploring the factors that affect reaction rate in much more detail as we go through the chapter. The rate laws at first glance appear to be the trickiest, yet I find kids to be very, very strong with them.